right, let's get in and look at some example problems. So we've seen already in the discrete time case that we have this is our response, a to the t, and so we again have seen that if a is greater than 0, that is, so notice in this case, this is our eigenvalue for our system. In this case, a is greater than 0 in magnitude, we get a divergent response. If a is equal to 1 in magnitude, so for example, if x of t plus 1 is equal to x of t the next time will just be the next time x of t will be the same as x of t at this time, and so it'll just stay constant. And if a is of magnitude less than 1, then each time I will multiply by something less than 1, which means x of t plus 1 will be smaller than x of t, and we get divergence. So we have that. We have a similar kind of situation in the continuous time. Okay, divergence if in the instability region, when the real parts of the eigenvalues are less than are in the right half plane, that is, they're positive. When the real part is equal to 0, we have constant magnitude, and when the real part is less than 0, we have a decaying response. We've also seen that the phase plane can illustrate the significance of the vector field and how the vector field affects the response. And so we have this vector field, and we're showing, starting from various initial conditions, what the response is using something called a comet plot. So this comet plot you can use in, it's just comet. There's also a 3D version of the comet plot. So that's kind of a fun little tool. With the phase plane, we have the various matrices that affect the phase plane response. So let me start over again. So notice here I have the 2 over here in the x2, and so things converge this way before they converge that way. Changing them around, they converge this way before they converge that way, and so forth. And so we've seen how the various pole locations or eigenvalue locations affect the convergence, and we can get convergence happening in a number of different ways. We also saw the different notions of stability associated with this. The weakest form of stability is stability in the sense of Lyapunov. So here's an example of stability in the sense of Lyapunov. So I'm going to start, my initial condition is going to start within this circle, and it will stay within this circle for all time. So let's see how it looks. So it's zooming along. Notice that this is the time axis, and then the other two axes are the axes of the state. Okay, so we'll take a look at those. So here it goes. So we're just simulating for some length of time. And so here I'm just moving the axes around to get a different perspective on it. So looking at it with respect to x1 versus time, x2 versus time, and now I'm plotting x1 versus x2, and we can see that it started within this circle and it stays within this circle. So this would be the circle associated with the delta. This would be the circle associated with epsilon. And so again, the notion of stability is if you start within this circle, you stay within this other circle. All right, here I have a system, and I'm going to simulate it with various initial conditions, all of which have norm equal to 1. So this is starting with an initial conditions on the ball, radius 1. And so here are the responses that I get. And so you can see that even though I started with a ball of radius 1, some of the responses actually, depending on where the initial conditions are, can be of magnitude greater than 1. Okay, so this is just a number of simulating with a number of initial conditions of magnitude equal to 1. Notice this is a 4th order system, so I can't show you a 3D plot of it, for example, because there are already 4 dimensions, and then there's time to consider. So we have that. All right, well, let's have some fun with systems. Woohoo! Fun. All right, so here we have a bunch of constants. All right, there's a lot of stuff going on here. N1 and N2. So we're going to we're going to start with n1 and n2 as integers, and based on those numbers, we have all of this stuff that's going on that's associated with that. Okay, so those two numbers basically determine what's going on. Now, if you've ever seen spirographs, okay, spirographs, well, basically what a spirograph is where you start off with two gears, and they mesh together, and you have a pan that's in there, and you start, and as you go around, it draws these nice little pictures. And so basically N1 and N2 are the gear ratios of those two gears, which is basically what you're starting with. And so you have two things. You have the gear ratio, and then you have the initial condition. The initial condition is how do you orient the gear, one gear within the other gear to start off with. So we define now our A matrix and our C matrix. Notice that our A matrix is of dimension 4 by 4. Our C matrix is of dimension 3. Okay, so we actually have fewer dimensions. And so this is our system. Notice there's no input to our system. We're going to just start with initial conditions, and we're going to look at some of the outputs. So here are some of the outputs for that. And what do we get? We get spirographs. So this is a comet plot for the response of the system for a particular value of N1 and N2. And so as we go through, we can see it is zooming around, and it's doing stuff. In this case, the way the eigenvalues are chosen, they're all chosen to be on the imaginary axis. Okay, so as a result, we get periodic type of signals. And so this signal is actually periodic, although it's not obvious because it hasn't repeated yet. Okay, it has a fairly long period, and its period is such that it goes through a lot of stuff before it completes. Now, what we're looking at here is actually a two-dimensional version of the state space, or rather, it's the output. But remember, the output actually had three variables associated with it. The x, y, and has three outputs. And so we're only looking at two of the outputs. So now we're going to shift the plot in 3D. And so this is what it looks like when you shift the plot in 3D. It doesn't look at all like that nice fancy rosette we had until we look at it from a particular perspective of two of the variables. Let's look at another one. So in this case, we have what looks like a star-ish type response. And again, this uses the same system. The only difference is the ends and the initial condition. And so, and notice when I move it around in 3D, I get all kinds of, it looks very different than when we look at it from this perspective. So here we're just repeating it again, just so you can kind of see what's going on. So notice it doesn't actually have any sharp edges at all. It's actually very round and curvy, but when you look at it from certain angles, it looks pointy. Kind of weird, huh? All right. Here is an example of a system that is asymptotically stable but not exponentially stable. So x dot is equal to all of this, and g is some function of time that satisfies this condition. G dot over g goes to 0 as t goes to infinity. Okay, so this is an example of a system that is asymptotically stable but not exponentially stable. So this is actually something like, well, it's not a time invariant system. So it's actually time varying, and so that's why it comes out this way. So basically, for systems that are not time invariant, you can have a system that is asymptotically stable but not exponentially stable. So this is not a nonlinear function, it's a time varying function, time varying system. Here's a nonlinear system. Notice that instead of having x, we have x cubed, so that's a nonlinear function of x. So this nonlinear system, starting off with this initial condition, has this solution. Okay, so notice t is in the denominator, And so we can show that for any fixed value of a greater than 10 and b greater than 0, that there is a time t naught such that the response of the system is less than x of, so this exponential becomes less than x for all t time after that. So this system is asymptotically stable. As t goes to infinity, this quantity goes to 0. However, it is not exponentially stable. That is, I can always find an exponential function so that this thing becomes less than that. Okay, so I'm sorry, so that this decays faster than this. So even if this starts off being greater than x of t, eventually it converges faster than this. Okay, and so here's an example of what that looks like. So here's x of t. X of t is converging, but notice, look how slowly it converges. Whereas if I have an exponential function, it'll always go converge faster than this will. Notice this function actually does converge to 0, but it takes so long to converge to 0. Whereas any exponential function will always converge faster. So again, this kind of thing cannot happen with linear systems, but it's important to understand that first of all, real systems, many real systems are in fact nonlinear systems, and so we need to keep that in mind. But also, so it's important to understand what's going on for nonlinear systems as well. So here I have a system, and I'm gonna, again, I have my ball of initial conditions that I start with, and notice in this case, the system stays within an envelope. Okay, and so here I have a number of responses for different initial conditions, and so there is an envelope such that for any x with norm of 1, I will always stay within that envelope. Notice that some of these guys come really close to the envelope, okay, but none of them exceed the envelope. None of them go outside the envelope. So this is the so before, when I showed the ball of initial conditions and the responses associated with those, I had a system that was stable in the sense of Lyapunov, but it was not exponentially stable. So this one clearly is exponentially stable. There's an envelope that I stay within. In terms of stability, we can have what's called an attractive equilibrium that's not at the origin. Okay, so here's the vector field, and I can see that it's an attractive vector field. I can also have an attractive unstable equilibrium. So when you have nonlinear systems, you can get all kinds of weird things happening. Okay, so here this system describes what I'm talking about. So this is one way of putting it. This is in polar coordinates. This is in rectangular coordinates. Okay, and so this is the kind of response that we get. So here is our equilibrium point. Okay, and so here are some example responses for the system. So notice that all of the systems or signals converge here. But the reason this is called an unstable equilibrium is because if I start really close to this point, it won't go directly to that. It'll go it'll go away from it first, and then it'll come back. So it's actually an attractive unstable equilibrium. That is, it actually attracts things, but it attracts them in a certain direction. So that's a consequence of the system being nonlinear. So these are some examples of stability of systems. So thanks for watching.